Hello and welcome to the Avid Technology Podcast with me, Ryan Morn. So today's podcast is about an electric and hybrid vehicle powertrain topology that we've mentioned a few times in different conference presentations and things like that. And in fact, I did a presentation at a conference earlier this year just on this topic. And we get a few people asking us exactly what we mean by this. And the question keeps coming up again and again. So we thought what we would do is turn this into a specific podcast episode for you. So that's what it's going to be about. Tri-voltage powertrain architectures. So basically, as electric and hybrid vehicles are becoming more widespread, people are looking at ways to improve performance and efficiency. One method that is attracting some attention is this tri-voltage architecture. And what we're going to talk about today is what does that mean? How does it help? And is it something that you should be thinking about? So let's start off with just with thinking about where we've kind of come from and where we're going to with electric and hybrid vehicles. It's not that long ago, literally within my kind of career at Avid, that we used to be talking about milk floats all the time. And so to people who don't live in the UK, a milk float was one of the earliest kind of types of electric vehicles that a lot of people would see all the time. So a milk float was used by the milkman to deliver milk in the morning, and it was electric because that meant it was really quiet. So you didn't have a big chuggy diesel engine in the 1960s thumping away and waking everyone up while the milkman was driving around putting the bottles of milk out. And it's a sound that I can really remember from my childhood, is the sort of whir of the milk float as it moves around, and the chink, chink, chink of the bottles clinking against each other. I believe there are some clips of this on the internet, so if you're that interested, do go and have a look. It's quite a distinctive sound. So that was the good bit about milk floats. The bad bit about milk floats is they were really slow, and they were always exceptionally ugly and quite unwieldy things. But even 10 years ago, you would have people in conversation start to talk to you about milk floats. But it's come on, it's such a long way since then. So, we've got so many great EVs on the market. Certain company in California has been quite good at that. Lots of other companies coming on the scene now, some really, really good EVs. Everything, from the Nissan Leaf up to Tesla Model S, the new Kona coming out. Really excited about that. There's all sorts of really good sort of practical EVs on the market now. Exciting EVs, sexy EVs. There's something for everyone. And then right at the top end, there's this whole other sort of area of that's emerged, which is the electric hypercar. So it does sort of fly in the face a little bit of the quest for electrification to save the planet. But basically what some really good people have realised is that you can make an awesome car, a fantastic powertrain. All of that low-speed torque from the electric motor just makes the vehicle accelerate like it's going out of fashion. You could make a really, really good high-performance vehicle with a hybrid or even a fully electric powertrain. So the good guys at Rimac doing fully electric. And then you've got some absolutely absurd hybrid powertrains out there. Everything from Koenigsegg to McLaren and lots of other OEMs in between. And there is a trend in the market where more and more high-performance vehicle manufacturers are turning to hybrids. And that's partly because it's a pretty excellent way of getting that performance. It's also partly to do with emissions compliance on these high-performance engines. But, it's quite remarkable, really, that in 10 years we've gone from sort of talking about these really low-performance, pretty rubbish milk floats to now having like $2 million hypercars that are electric because electric has been shown to be the best way of doing it. So just kind of think about where we've come from and where we've gone to. And, there'll be more and more and more electric vehicles come out onto the market. And as more vehicles come out, manufacturers are going to seek ways of improving them, of making them more efficient and getting more out of them. And this applies to cars, to trucks, to buses, all kinds of things. So there's been a lot of development in EVs, and there's a lot more development to come in EVs and hybrids. There's another kind of system coming out. So this is the sort of not quite soft hybrids, so mild hybrids. So you might have heard people talk about 48 volt mild hybrids. Anyone who's in the automotive industry will absolutely know about 48 volt mild hybrids. So basically what a 48 volt system is, it's not a full hybrid or EV. It's a lower performance system. It's 48 volts. So actually, if we go back far enough, so I think around 1990, it was 42 volts, and that was for a particular reason to do with putting lead batteries together and stuff. Now that's creeped up a little bit to 48 volts. But basically, the reason for that is that what we're trying to do is keep the voltage under 60. So kind of 48 is actually really the nominal voltage. It should be a less than 60 volt system, but that doesn't quite roll off the tongue as easily. So we talk about 48 volt systems. Now, keeping the voltage below 60 volts has a lot of advantages. It completely transforms all of the safety requirements that are required for the vehicle, for the electrical system. So if you're building a high voltage, like a 300, 400, even 800 volt system, there's absolutely oodles of stuff you need to do to make sure that stays safe, to make sure that you never end up with high voltage going to the body. The cables are really expensive, double insulated, armoured cables, shielding. You've got to have a leakage detection. You've got to have all sorts of things that add costs to the vehicle. Just the high voltage connector systems are massively expensive. But staying down at 48 volts means that we can get some of the advantages, but basically we don't have all of the costs. And the rule of thumb that people talk about is a 48 volt mild hybrid will give you, depending on who you're listening to, between 70 and 80% of the benefits of a full hybrid, but for between 20 and 30% of the cost of the full hybrid. So that's kind of pushing a lot of development on the 48 volt systems. Now, if you are not an engineer, you might be thinking, well, why on earth? Why does that matter? So what? Why do I care? Basically, a normal car, and actually some commercial vehicles and heavy-duty vehicles, they have a 12 volt electrical system. And with 12 volts, you're quite severely limited in terms of what you can do from a power point of view, because basically power equals volts times current. So for a given amount of power, if I want 1 kilowatt at 12 volts, I've got a given amount of current, and I know exactly what it is, but I'm quite restricted on the amount of current that I can pass through conductors, so cables, through devices, because basically current causes what is known as ohmic losses. So the square of the current times the resistance of the thing the current is passing through creates ohmic losses, which basically generates heat. The device gets hot. So we're limited in terms of what we can do. Now, obviously, if I go up to 48 volts from 12 volts, and go back to that equation, P equals volts times current. So if I've now times my volts by 4, I can divide my current by 4, so I quarter the amount of current that I need for the same amount of power. So that 1 kilowatt device, which at 12 volts would have been completely impractical because it would have had a crazy amount of current going through it, now actually is practical with 48 volts. I can do an awful lot more on the system, which means I can actually do a good amount of energy recovery under braking. I can do regen braking. I can put a good amount of torque into the system under acceleration. I can use 48 volts to drive all sorts of different accessory systems on the vehicle, the fans, the cooling pumps, all sorts of different things. And we've talked about that before. We'll talk about it again. The 48 volt mild hybrid, it's got a lot of benefits for passenger car. And in fact, some people are saying that essentially you need to have 48 volts to comply, to pass the RDE regulations. Now, a bit of debate around that because some other people can get around it with the methods, but definitely the real driving environment testing is kind of pushing more and more electrification on the vehicle and leading to more 48 volt mild hybrids. So there's a lot of potential for a 48 volt mild hybrid system by itself, okay? But we were already talking about these really high performance EVs, about trucks, about buses, and how we've come on such a long way. So the 48 volts is basically a system at a more basic level. But then a tri-voltage system is a combination. It's the child of 48 volt architecture and a high voltage EV and HEV architecture. So what we're doing with a tri-voltage architecture is we are putting together the best of both systems. So let's think about, we've got a high voltage EV. So let's say we've got 400 volts DC voltage, and we're going to use that 400 volt for the traction system and maybe for one or two other ancillary components. So at 400 volts, it's great. We've got less current going into the devices. I mean, the traction motor at 12 volts wouldn't be possible at all. But 400 volts. But we've got all the safety considerations to take into account. So we're not going to put every electrical device on the vehicle at 400 volts because basically it's going to be really, really expensive to do that. So there's going to be lots of other electrical devices on the vehicle that are still at 12 volts potentially. Now, what we would do in a tri-voltage system is we'd take all of those high power consumers off the 12 volt system and we'd put them onto a 48 volt system. So we'd have 12 volts on the vehicle for basically all the low power stuff. So anything that doesn't require a lot of current, it's going to be cheap, it's going to be low power just to keep that at 12 volts. So that'd be things like your infotainment, probably your light clusters, anything that doesn't require a lot of power. Then our accessories that we've got at a higher power level, so taking maybe 500 watts, 1 kilowatt, 2 kilowatts out of the system. So various different components there, things like coolant pumps, things like electric fans, things like thermal management components. Even got people talking about putting things like seat heaters at 48 volts. All of those higher power consumers on the system, where they're more than, we get an advantage basically in terms of we could put those devices onto a 48 volt system, and then we keep the really high power stuff sitting on our high voltage, so straight from the battery system. So this gives us, adopting this tri-voltage architecture gives us several advantages. So any device that we've taken from 12 volts and we've put it up to 48 volts, we can immediately make that device lighter because we can take copper out of it. We're going to make the cables that run to it lighter because they're having to carry less current. So basically we can take weight out of the system. We can have higher power devices, so that might be important in some applications. So for example, if you're doing something like an electric truck in North America, the base truck architecture is going to be 12 volts. And you're probably going to hit a problem in terms of, if I want to run that truck with an electric powertrain, I'm going to need a lot of cooling fans and cooling pumps and other accessories. I don't want to put them at high voltage because it's going to make them really, really expensive, but I can't run them. I just can't run them at 12 volts. There's just not enough power available. So the step there is to introduce this third voltage to the system, and we run all of those consumers on 48 volts. So we get a more efficient component. We can take copper out of the system compared to having them at 12 volts. We save a lot of cost compared to having these things at high voltage. If we had them running on the high voltage system, I often say to people, the connector would cost more than the component if they were all running at high voltage, because we need to protect all the wiring. We're going to have return harness in because you can't connect devices to the ground with high voltage, etc., etc. Lots of issues that add cost of going to high voltage. So it's better to have them on the 48 volt system. And then the final benefit is, if we had a lot of power on the 12 volt system, we will have a device called a DC-DC converter sitting there, and that will be converting the high voltage down into 12 volts. Now, if we can reduce the amount of current going onto the 12 volt system, we can make that DC-DC converter smaller and lighter and more efficient. So the thing that really hammers a DC-DC converter is the high current at 12 volts coming out of it. So effectively the ohmic losses in the device from the 12 volt system. So if we were able to basically really minimize our 12 volt power consumption on the vehicle, we can make the DC-DC converter, which is quite a significant cost item, smaller, because basically a 48 volt DC-DC converter will require less copper for the same amount of power than a 12 volt one. So an integrated high voltage to 48 and then to 12 volts, so like a two-step DC-DC converter to give you that tri-voltage architecture, will be lighter and more efficient than the equivalent powered 12 volt only DC-DC converter. So it gives a further opportunity to take some weight and mass out of the system, which is what people are striving towards now. And especially there's some applications where really tri-voltage is starting to find its feet. So if we're talking about really high performance electric vehicles, so into that supercar territory, these really high performance vehicles, they have a large parasitic load, but then they live for the performance. They are high performance vehicles, so anything that we can do to make them more efficient, more effective, and basically improve the performance, we're gonna try and do. So tri voltage is coming in on several high performance vehicles, and we're involved in a couple of those. The other application where it's really useful to have the tri-voltage architecture is if you've got a high-power vehicle that you're converting into a hybrid or an electric. So that would be basically you have a high-power vehicle like a bus or a truck or an off-highway machine. Particularly if the base electrical system was 12 volts. So it's less bad with a 24 volts base electrical system, but it still can be an issue. So particularly 12 volt base electrical system, and actually even in very big trucks in North America have 12 volts base electrical systems. They don't have 24 volts like trucks in Europe have. So on these high power vehicles, large vehicles like that, we're going to have a lot of parasitic loads on the vehicle. So big cooling system, other componentry sitting there on the vehicle, things like air compressors, power steering, pumps, all sorts of parasitic loads, and moving those loads onto 48 volts, it might be essential, to be honest. You might not be able to do it at all on 12 volts if it had a 12 volt base architecture on my truck or my off-highway machine, but it's going to give me a big performance advantage even if it was at 24 volts going up to 48, because we're at least halving the current. But if it was originally a 12 volt vehicle, we're quartering it, like we said before, and we don't have to incur the very high costs of going up to high voltage for these accessories. So on those kind of higher power applications, the tri-voltage architecture works really nicely. So it's not something that you would probably typically do on a normal passenger car without some very special reasons, but on a full EV, on a high performance supercar, kind of very fast, very powerful vehicle, or a commercial vehicle or an off-highway vehicle, tri-voltage architecture can bring a lot of benefits. And we're seeing pull from the market. So I hope that's answered the question in terms of these people that have been asking me, what are you talking about when you say tri-voltage architecture? So that is it. That is what we mean when we're talking about tri-voltage architecture. It's a combination of a 12 volt, 48 volt, and a high voltage system. The reason you would do it is because you can take weight out of the vehicle powertrain, and you can make the powertrain more efficient and potentially take some cost out. If you had some of those accessories on the high voltage side, you put them onto the 48 volt instead of being on high voltage, and they will be significantly less expensive than the high voltage equivalents. So that is why you would do it. So I hope that's been really useful. As ever, if you could hit like, if you could leave us a rating and a comment, depending on which platform you're listening to us on, I would really, really appreciate it. That would be fantastic. Don't forget to subscribe to the channel, and really looking forward to speaking to you again soon. We've got some really exciting podcast episodes coming. So thanks very much for listening. That's all for today.